It's a very interesting situation where both the phenomenon of interference, diffraction, etc., according to which we treat light as a wave, fails to explain certain phenomena like photoelectric effect, Raman effect, Compton effect, and so on. And therefore, a new theory had to be developed, and you know, the theory developed by Max Planck is the quantum theory of radiation. So light now is behaving like a wave in some cases to explain the phenomenon of I'm not sure. ಇಲ್ಲಪ್ಪ ಇದು
ಇದರಲ್ಲಿ ನೆಕ್ಸ್ಟ್
Okay. Now, whatever I have mentioned, in fact, is here. Light is a form of energy, and rectilinear propagation of light gives us various phenomenon. For example, the formation of shadows is the best example for the rectilinear propagation of light. Light travels in straight lines. But, of course, the study of light, as I mentioned, is called optics, and we divide the study into two branches, the geometrical optics and the physical optics. Geometrical optics, as I mentioned, discusses formation of images, shadows, lenses, mirrors, prism, optical instruments like telescope, microscope. All these are based on rectilinear propagation. And then in physical optics, we discuss about the nature of light, the propagation of light as light energy, how exactly light energy is propagated as a wave, and the wave nature is discussed. And here, there are two theories. As I mentioned, of course, there are four theories of light, and the earlier theory was the corpuscular theory, and in fact, the other phenomenon which I have mentioned, interference, diffraction, etc. Now, various theories of light have been developed to understand light. Now, what exactly light is? The first attempt to understand the nature of light was done by Isaac Newton, who suggested that light is made up of tiny particles. He called them as corpuscles. And this theory is called the corpuscular theory of light, according to which light is made up of small tiny particles, and you know, whenever there is these particles have no mass. These corpuscles are massless particles. When they don't have any mass, you know that they are not attracted by gravitational force. So no external force. So under the influence of no force, these particles which are emitted with a velocity continues to travel with that velocity. So light particles travel with the same velocity from a source. All light particles travel with the same velocity emitted from the source because they don't have any attractive force as mass is zero. According to Newton's law of gravitation, you know that the force, mass comes because of the force. And G is mm by r square, gmm by r squared. And since one mass is zero, there is no force on this. When there is no force, the particles travel under the influence of, say, no force, you know that you consider the first law of Newton. When there is no force, particles travel continuously with the same velocity. So all these particles, corpuscles, travel with the same velocity, and that, of course, on the basis of this, Newton explains the phenomenon of reflection, refraction. That is all right. To explain reflection, Newton assumes that the surface, the mirror, has a property called repulsion. So when these particles approach the mirror, they will be repelled, and this repulsive force is perpendicular to the surface, and therefore they are repelled, and with the same velocity they are repelled back. Therefore, the velocity before the velocity of the incident ray and the velocity of the reflected ray are one and the same. And of course, he gives a mathematical formula for proving that I equals R, angle of incidence equals angle of reflection. Similarly, Newton explains the phenomenon of refraction. Here, to explain the phenomenon of refraction, Newton assumes an attractive force. See the problem. To explain reflection, there is a repulsive force. To explain refraction, there is an attractive force. And the problem here is when there is a force of attraction in the denser medium, for example, when the light travels from air to a denser medium, there is attraction. And because of this force, the corpuscles should travel with a larger velocity because there is an additional force. In other words, the velocity of light in a denser medium should be more than the velocity in the rarer medium. But we know experiments show that the velocity of light is more in a rarer medium than in a denser medium. And therefore, this was a major defect in corpuscular theory. And now, to explain reflection, a repulsive force. To explain attraction, refraction, an attractive force. Now, there is another situation, interesting situation. That light sometimes shows both reflection and refraction, simultaneous reflection and refraction. That is, if you take a partially polished surface, if you make light incident on that, part of it is light is reflected, part of it is refracted. In other words, there is simultaneous reflection and refraction. So if there is simultaneous reflection and refraction, what type of force we should assume, whether it is repulsive force or attractive force. So he was unable to explain this. He says simply, this is fits of imagination. So there is no explanation for the simultaneous reflection and refraction according to corpuscular theory of light. Simultaneously with the proposal of corpuscular theory, there was another theory almost simultaneously by Christian Huygens. He suggested that light is propagated as a wave, not as a particle. Wave, just like, for example, sound waves, water waves, seismic waves, etc., light also travels in the form of waves. The light energy is propagated from one point to the other point in the form of waves. Now, if we assume that light travels in the form of waves, for the propagation of sound or any other wave, for example, which I mentioned, water waves, seismic waves, etc., a medium is necessary. For sound to propagate, air or any other medium, solid, liquid or gaseous medium is required. But for light, we know that no medium is required because we are getting light from distant objects like stars, planets, etc. And we know that only up to a certain height the atmosphere is there, and beyond that there is nothing. There is vacuum. In other words, light travels in vacuum also. How to explain this? This was a problem. And therefore, to overcome this, people assumed that there exists a medium called ether, right? Which is an all-pervading, omnipresent medium, which is there everywhere. And as Einstein says, no doors are closed for ether, it is present everywhere. So if such is the situation, light is propagating from even in vacuum. But in vacuum there is no meaning for vacuum now because there is a medium called ether. Now, there were experiments to measure to detect the existence of ether by, of course, as you know, Michelson and Morley, who conducted experiments. In fact, Michelson and Morley conducted the experiment to detect the existence of ether for 40 years. They conducted experiments for 40 years, from 1888 to 1928, for 40 years. And they conducted the experiment during day, morning, evening, afternoon, say during summer, winter, all seasons, so that if at all this medium exists, it should have some effect on the velocity of light. That means you know that velocity of light is very large, 3 into 10 to the power of 10 meters per second, right? If that is the case, then if it is traveling in a medium, then the velocity is affected by the presence of the medium. Because if we consider, for example, that we are also moving in the direction of the medium, the velocity will be less. Velocity will be more, sorry. On the other hand, if we are going against, imagine, for example, you are swimming in the direction of flow of the water. Your speed will be added by the velocity of the stream. On the other hand, if you are going against the stream, you are obstructed. Therefore, your velocity decreases. Similarly, if light is propagated with a certain velocity in the medium ether, and if the medium ether is supporting this, its velocity will be more. If the medium is opposing this, the velocity will be less. Therefore, what happens? The velocity of light depends on the direction of flow, or the direction in which the observer is observing. In other words, the velocity of light depends on the observer. This was the conclusion which they thought, and therefore they tried to determine the velocity of the ether which is attached to Earth. In fact, they assumed that the ether is attached to the Earth. So, if the velocity of light is different from the velocity of the ether, then the velocity we measure in different cases, in different times, during different seasons, they must be different. But the experiment, which was very accurate experiment of Michelson and Morley, did not give any idea about the existence of ether. Therefore, it was discarded. Later on, you know that a new theory was given by James Clerk Maxwell, which is now called the electromagnetic theory. Now, he suggested that light is made up of electric and magnetic vectors. That is, the changing electric and magnetic vectors, which are changing at a very rapid speed, is responsible for propagating or this light. So, light is considered as a phenomenon in which there is a rapid change in the electric and magnetic fields in the medium. This does not require any medium at all. So, the need for the existence of a medium was discarded, and Maxwell actually showed that these electromagnetic waves are nothing but light waves. Electromagnetic waves and light are one and the same. And in fact, he unified the electromagnetism and optics. This is the second most important unification in the history of physics. The first unification was by Newton, who showed that the gravitational force which is responsible for the falling of an apple is the same as the gravitational force that is responsible to hold the planets in their orbits. So he unified what we call as terrestrial gravity with the celestial gravity. That is the first unification. The second unification of electricity and magnetism and optics, was by James Clerk Maxwell. And Maxwell's theory, of course, is very complicated in the sense at this level, it is not easy to understand because it is purely mathematical. He gives, in fact, 4 differential equations, second order differential equations, which explains the complete, along with that, of course, which explains the complete behavior of all the optical phenomenon, except, of course, the photoelectric effect. And that gave rise to the new theory, the quantum theory of radiation, developed by Max Planck in 1900. In fact, it may be a strange coincidence. On 14th December 1900, Max Planck presented his theory to the audience, the scientific community, where this quantum theory of radiation was proposed. And today is December 14th. Of course, it is a strange coincidence, that's all. Now, according to quantum theory, you know that light is made up of, again, small packets of energy called quanta or photons. and they travel with, they also have no mass. Rest mass, of course, that is one important point. They don't have rest mass. The rest mass of photons is zero. They always travel with the velocity of light. You cannot reduce the velocity of the photons less than the velocity of light. They always travel with that velocity. So this is about, these are the 4 different theories of light. And that means to say, people struggle to understand the nature of light, what exactly light is made up of, and how exactly the light energy is propagated. Sorry, in fact, the other way I should. See, then comes what is called the dual nature. Later, by 1925, people showed, in fact, by 1905 itself, and Einstein explained the phenomenon of photoelectric effect. He suggested that light is made up of packets of energy. That is what Max Planck used. The same idea was used by Einstein to explain the phenomenon of photoelectric effect. And therefore, light behaves like waves in explaining the phenomenon like interference, diffraction, polarization, etc. Reflection, refraction, all these can be explained on the basis of wave theory. But to explain the phenomenon like photoelectric effect, Raman effect, Compton effect, and also the spectra emitted by various elements, etc., you have to treat light as being made up of packets of energy, the quanta. So it is showing dual nature. So it behaves both as a particle and as a wave. Similarly, in fact, de Broglie in 1925 suggested that material particles like electrons, protons, etc., also behave like waves. They were called the matter waves, and he derived an expression for the matter waves, which is now lambda is h by p, where h is the Planck's constant and p is the momentum of the particle. So you can see here light source. If you imagine that as a particle, if you have a barrier, these particles are cut off by the barrier. Only those which are, where there is no obstruction, the particles move. On the other hand, if you think of a light source, even if the barrier is there, if you imagine that light as a wave, it bends. That is diffraction. The rectilinear propagation is now an approximation of the wave. The wave, it propagates, light propagates as a wave. But we are not able to see this as a wave because of the sharpness in wavelength. You know that the wavelength of the visible light, you know the spectrum, electromagnetic spectrum. And if you consider the visible region, that is the visible light, which we say red and violet, the VIBGYOR, that has wavelengths between 400 to 700 nanometers. And we have, in fact, you know that radiations having wavelengths less than this one, like ultraviolet radiations, and larger than the visible radiation, like the infrared radiation, and beyond that also you have other types of radiation. So it's an electromagnetic spectrum. So, behavior of light is of dual nature. But can we detect this dual nature simultaneously? See, in the phenomenon of interference, diffraction, etc., you treat light as a wave. To explain other phenomenon which I mentioned, photoelectric effect, etc., you treat light as a particle or quanta. So can we design an experiment wherein we can show light both as a particle and as a wave simultaneously? And the answer is no, because these two behavior are like the two sides of a coin, right? Head, of course, if you call head as the particle nature and the tail as the wave nature, you cannot see both head and tail simultaneously if you hold a coin. You can see the image if you have a mirror, but it is a virtual position. So simultaneously, it is impossible to see both the properties, property of a wave, property of a particle of light. So if we design, in fact, it is very clearly mentioned, if we design an experiment to detect the particle nature of light, the wave nature disappears. On the other hand, if we design an experiment to detect the wave nature, the particle nature disappears. So simultaneously, it is impossible to detect the particle nature and the wave nature of light. Therefore, in fact, this was a very difficult proposition for scientists. In fact, one of Einstein's close worker, Benesch Hoffman, who worked with Einstein for nearly 25 years, says that on Mondays, Wednesdays, and Fridays, light behaves as a wave. Tuesdays, Thursdays, and Saturdays, it behaves as a particle. And Sundays, it goes to the church to pray. How should it behave the next week? So that is what the difficulty is, to understand the nature of light. So as I mentioned, these are the various phenomena exhibited by light: reflection, refraction, simultaneous reflection, total internal reflection, interference, etc. Now, from my discussion with some of my friends, I thought that I should discuss about the interference. Now, I'll stop here in the sense, I will ask the feedback, what exactly you need from me hereafter. So I have given you the basic introduction to light and the various theories briefly, right? Now, what is it that you want? What is the difficulty that you are facing in teaching this particular topic, optics, to the students? If you have difficulties, if you have any questions, you please, otherwise I will be giving, this will be an one-way traffic, right? I have some ideas, I will be going on discussing that which may not be interesting to you. Of course, my presentation may appear to be interesting, but that is not useful to you. Interest is different from usefulness. So please let me know what exactly you are expecting from my talk. Don't hesitate. Yes, sir. Yes.
Different colors is due to different wavelengths.
Yes.
When the red ray, when it travels from air to water, certainly there will be a decrease in the wavelength,
Yes.
not change in the color. How to convince this student?
See, the velocity of the wave is equal to n lambda or f lambda, frequency into wavelength. And the frequency is a fundamental character of the wave. And when the light is traveling from one medium to the other medium, the velocity is changing, because if it is going from a rarer medium to a denser medium, its velocity decreases, right? When velocity decreases, frequency is fixed. Therefore, when the frequency is fixed, it is the wavelength which changes, because V is f lambda and f is constant. So as V changes, lambda changes. Therefore, it changes its color. But the change in frequency is so small. In fact, when I say red, we say that it has got a wavelength of about 700 nanometers approximately. But exact 700 is not, it's a range. It's a range, small range. So when I say, for example, now this is a very interesting point. Many of the people here are wearing different colored cloths, right? Different colors dress. Now if I say some of them have blue color, that blue is not well defined, because there are different types of blues. Why? The frequency, the range of frequency of blue light is over a certain wavelength, certain range. So when light is traveling from one medium to the other medium, the color changes, right? But the change in wavelength is so small that we cannot detect that to be completely different from the red light it is. So, but measurements show that the frequency is constant, the velocity has changed. Therefore, correspondingly, you can calculate. Even if you calculate, for example, the mu is velocity in air by velocity in the medium. And for example, if you take glass, mu is about 1.5. And if you use, for example, the wavelength of red light and calculate using this value of the mu, the change in the wavelength, it will be very small, and it is very difficult to analyze that it is but there is a change. Velocity measurement shows that there is a change in frequency, a change in wavelength, not the frequency. Therefore, you see, you cannot show them the different color, right? Now, if at all you have to show that it is a different color, then the velocity should be very large. The what I should say. In fact, there is another important effect: the motion of the source and the observer. You are familiar with what we call the Doppler effect. Doppler effect. When you have a source which is moving with some velocity, its velocity, this frequency changes, its color changes, right? The famous joke you may be knowing, the judge, when a particular scientist was charged for overspeeding in a signal light, he was brought to the court, and a case was filed on him, and the reason was that he has jumped the signal. But the scientist, of course, being a scientist, he said he knew the Doppler effect. So I was traveling very fast, therefore red appeared green for me, and therefore I crossed. So it is not, that means to say, the change is, and of course, he was fined because if you have to see that red appear as green, you should be traveling over speed. And not only you have jumped the signal, you are over speeding, and therefore you will be fined double. So that is the situation. So to convince the students, the only thing is mathematically you can show that this change has happened, and we are unable to detect, our eyes are not so sensitive to detect such small changes in wavelengths. Yes.
Differences between optical density and mass density.
Optical density is the ratio of the velocities. For example, optical refractive index, you call it as optical density, which is the ratio of the velocity of the light in air or vacuum and the velocity of light in the medium. And mass density is for the medium, for example, if you think of light, it is the medium which matters, transparent medium which matters, right? So when you think of light propagating from one medium to other medium, it is the transparent medium, it is not opaque. Mass density is about the body, the mass of the body, the mechanical mass, what you call as mass by volume. Mass by volume is the mechanical, what you call as mass density. So that is nothing to do with optical density. Optical density is the ratio of the velocities, whereas no velocity, nothing is required. And so mass over volume is the normal density that we define, right? Yes. Yeah.
All of us almost learned how to teach students from the exam point of view.
Yes.
Make them score marks.
Yes.
So we are aiming to produce results. That way, to some extent, teachers are expertise. But the challenge teachers like us face: how do we make optics very interesting? Making optics interesting is a challenge. So that is what I wanted to ask you. And I have an opinion about what sir was asking. That when light enters into a different medium, maybe like glass or water, the wavelength definitely decreases. Probably if 8,000 angstrom red light enters into glass, it would probably become around 5,300, 5,400 angstrom, would become into a green light. But when we observe it from outside, doesn't look like green light is what sir was actually asking, I believe. So in that way, if we are not able to observe green light, again we are observing from air only. If light travels from water once again, comes back to air, it appears like red only, it doesn't appear like green.
Yeah, fine.
This is what I believe.
Very good answer. And of course, I just add to this one. Fine. See, imagine. Yeah, yes. No. It has changed. Correct. You also if you go to that medium. Now the question, the answer is this. Wait. Your answer is this. Let us say light is going from air to water. Now imagine that you are inside water. You will not. You will not, because the change is so small. It is not. it appears, because the change is not that effective. That, yes. ಏನು ಗೋವಿಂದ ಏನು ಹೇಳ್ತೀರಾ ನೀವು ಗೋವಿಂದ ಸಿ
If I just want to add, we have to be very careful when we discuss about what we feel and what we measure. Feeling is not physics, measurement is physics, and color is not measurement. Color is a subjective feeling which happens in the brain. And in physics, we'll talk about color because we have seen color. For example, I'm not very sure. Some animals like cow, we can see only black and white. I have read somewhere, I have to verify that. ಈಗ ಕೆಂಪಟ್ಟೆ ಹಾಕೊಂಡು ಹೊಡ್ಕೊಂಡು ಬರುತ್ತೆ ಅದೆಲ್ಲ ಹೇಳ್ತಾರ that may be wrong. Anyway, then what is more important is what causes the feeling of color. The feeling of color happens because of sensation in the retina. And in retina, what basically happens is very similar to photoelectric effect. And therefore, the excitation of cones, which are responsible for color, is dependent on frequency and not on wavelength. It depends on the energy of the photon. So when light goes to any medium, frequency does not change, and therefore color will not change. In a given medium, you can talk of different colors, different wavelength. In air, normally, when we don't specify, it is air. But when it goes from one medium to another, color should be represented by frequency, not by wavelength. So in glass, light has same energy, E equals h nu. It has become slow. That doesn't mean it has lost energy. One more point I just want to tell. For example, if a high school student asks, why is glass transparent? You cannot say light somehow sneaks through in between the atoms and therefore it doesn't find any obstruction. Because if you drop a piece of wood and glass into water, glass sinks, so it has more density. So obviously atoms should be more packed in glass. And if there are any spaces between the atoms, wood should have more spaces, but wood is not transparent. So I had some kind of an explanation which I told to some professor in Raman Institute. And he said in a crude level it is okay, there are different levels of understanding. So at the basic level of understanding, you can take it like this. If there is a big crowd of people, you throw a tennis ball from outside. If there is no crowd, the ball goes with the same speed. That's what happens, let us say, in vacuum for light. But if it is a crowd, then it cannot go through the crowd because somebody will collide with that. So we will say they are passing the ball, and the first person will catch the ball, throw it to the next person. He will catch it again, throw it to the next person. Finally, the last person throws out. So the ball comes out of the crowd with the same speed. But in between, on an average, it has slowed down because each person takes some time to catch it, hold it, and throw it to the next person. And something very exactly similar is happening in glass. The first atom on the surface will absorb light. It will re-emit to the next atom. And then that will re-emit to the next atom. So on an average in glass, it has slowed down because every atom takes some time to get excited and get relaxed. And that relaxation time actually is related to dielectric constant. And that is why refractive index has a connection to dielectric constant. So glass is transparent because we get a coordinated behavior in glass. That means each atom will not throw away the light in random direction. If that happens, it becomes scattering. So there is a coordinated thing, and to go further, you need electromagnetic equations and all. So finally, you can relate it to type of bonding, the electric constant and all. So that is why some materials where this can happen in coordination, light can go in the same line without getting scattered. And therefore, light has become slow in glass, not because it has lost energy. If it has really become slow because of something like retardation, then it cannot come out with the same speed. So it has not lost energy, So we have to convince the students to say that frequency causes color, not wavelength. And in a given medium, you can have different wavelengths for different colors. That is what we explain in this spectrum and all. But when there is a change of medium, you have to take color as standard because that is what remains constant. And as one of you said it, inside water, wavelength of red is equivalent to wavelength of green in air. But in water, that is the wavelength of red. So wavelength of red need not be same everywhere. Frequency of red should be same everywhere. And if frequency changes, you will find the difference in color. That's what happens even in gravitational redshift and other cases. So color, if you associate with frequency, then there is no problem. Okay, thank you. Yes.
Difficulty is actually not in, one thing is explaining, and the second thing is about convincing the students that such thing will actually happen. So one of the things that we can actually do is a simple experiment to show them that optical density is different from physical density. I'll give you two materials from which you can actually elicit this particular principle very clearly. So you take up...
before that, 1 second. Professor Govinda, of course, also did his PhD from Brahman Research Institute, and he is a professor of physics from Vijaya College. And he is Professor Achyuta, and he is, in fact, in the afternoon, he will show some beautiful experiments. He is an expert in experiments. Yes, go ahead.
Thank you, sir. Physical density is mass per volume. So you take up material, measure the mass, take some unit volume, and then you will know the ratio. So you will be able to find out the ratio there. So that's physical density. Turpentine, which you actually use to wash, paint. That actually is having lesser physical density, but more optical density. Now, how do you prove about optical density? You take light, shine it, it will change its path. That's only way we can actually talk about, light, it is going slow in a particular medium. One medium will slow ಹೋಗ್ತಿದೆ ಅಂತ explain ಮಾಡಕ್ಕೆ. We know that it will actually change its path. And now the question is, why should it change its path? It should change its path because it wants to come from one place to another place in the least time, which is Fermat's theorem. It has to come from one place to another place in the least time path. So idin ತೋರಿಸಿದ್ರೆ I think we will be able to convince them that physical density, first thing is, whenever we are talking about optics, especially refraction, talk about physical density and optical density, tell them that it is completely different. Physical density is, mass per unit volume, and optical density is the time taken by the light to go from one place to another place in the least time. It's in all physical phenomena that we actually see around, the object moving from one place to another place in the least distance path. Here in light, it is actually least time path. So that is somehow, I think, one of the ways of convincing. So, of course. Exactly. Yes, sir.
I just want to add, you can start from what I said as why glass is transparent, things like that. Then physical density is mass by volume, how much mass is packed up in a given volume, number of atoms, weight of each atom, things like that. But optical density is what light feels. So you can say how difficult it is for light to go through a particular medium, to what extent it becomes slow, and that is related to dielectric constant and non-mass. So that you can mention. Okay.
But 1 second. The concept of dielectric constant, others are very difficult to introduce at the PUC level. So it's all right. In fact, for people at the higher level, it is easier to say. But for the pre-university student, of course, he has done work in dielectrics, and that's why he is able to convince you. But yes, madam.
We still introduce dielectrics in PUC, in electrostatics.
Yes, I know that. 4 pi epsilon naught, etc. Right? That is there. But see, how we can relate this electromagnetism to optics is another important point, which of course we have to think of the Maxwell's equations. That is very difficult at that level. Anyway, thank you very much, Professor Govinda and Professor Achyuta. Then, yes, any other questions? So, yes. It's good. 1 second. It is, yeah.
Hello. Good afternoon, sir. So this is my first year for the PU board. While teaching the simple microscope, compound microscope, and telescope, we have the part related to the derivation for magnifying power. So can you teach some simple tricks how students can remember the derivation steps and all?
So I have, of course, not thought of those things. I have only mentioned linear propagation. Derivation, of course, is in a regular class.
Okay.
See, of course, I can tell you later. We can discuss that.
Okay.
But I cannot go on deriving here in this lecture.
Fine.
Right?
Okay,
Fine.
sir. Thank you.
Yeah. Give it, no problem. Yes? Yes, madam.
Also concept of diffraction.
Ah,
How to make it interesting and easy. Interference somehow they will understand.
okay.
But diffraction, by the time they learn diffraction, they will lose interest.
Yeah.
How to connect that to day-to-day life where we are using that concept?
See, diffraction is a phenomenon which is deviation from rectilinear propagation of light. See, straight line motion gives you the shadows. But if you observe the region below the shadow carefully, you see alternate dark and bright regions, right? So, the diffraction happens, for example, the size of the particle where or size of the medium where it bends is comparable with the wavelength of the light which is reflected. See, for example, the bending of sound waves is very easy. People outside can listen to me because the wavelength of sound waves is large. But the wavelength of light is very, very small, of the order of nanometers, you know. And therefore, for observing the bending of light, that phenomenon of diffraction, the surface which causes the diffraction or the region which causes the diffraction must be of the same order as that of the wavelength of light. So that is why, in fact, if you think of diffraction of X-rays, for example, with crystals, you know, when you pass X-rays through a crystal, you get diffraction pattern, right? Or if you think of the grating, diffraction grating, of course, you all know what a grating is. It consists of slits, very closely spaced slits. And roughly you know that the slit you have in about 1 centimeter, around 6,000 lines, roughly 15,000 lines per inch, like that. So you can find out what exactly the spacing between the two slits. And if you observe the diffraction pattern, if you pass the light through such a medium or such a system, then you will see the diffraction. So for the phenomenon of diffraction to happen, the first condition is that the object which produces the diffraction must be of the same order of the wavelength of light which produces the diffraction. But if you have sharp objects, for example, the diffraction by a wire, in fact, those of you who have done experiments, you may be remembering, see, if you think of a wire and make the monochromatic light fall on that, you will see diffraction pattern. Or if you see a fine sharp edge, like the edge of a blade, you can see the diffraction pattern. So the phenomenon of diffraction is because of the smallness in the wavelength of light. Phenomenon of diffraction of light is because of the smallness in the wavelength, and the bending happens when the size is comparable with the wavelength of the radiation. So, and see these diffraction halos and the different diffraction patterns. If you just think of a laser beam, for example, and pass it through, for example, a grating. In fact, the ordinary grating, in fact, there is a very interesting experiment which I think maybe Achyuta may be showing in the afternoon. If you think of a disc, that is cassette, and see there will be very close lines on that. In fact, it is estimated that about 720 lines will be there per millimeter. 720 lines per millimeter of that. So if you take a small piece of that and pass white light through that, you can see the diffraction pattern. In fact, you can make measurements also. There is a very interesting experiment which I think Achyuta, I don't know whether he is showing this or not this evening. This is a very wonderful experiment. So that's how, Achyuta, are you showing this experiment diffraction? Ade Raghavendra. Cassette. Illa. Okay. Anyway, he has got a beautiful experiment on that. Yeah, that's what. Show that. Very nice. Yes, madam. Okay. So the point is how to make the teaching interesting is purely individual, right? I cannot say I can make my teaching interesting because I weave stories into this one, the biographical sketches, like that. So it all depends on the teacher. How? Sorry, I think I should. So how to make teaching interesting is highly individualistic, right? And it depends on how much you have studied. That is very important. And day-to-day examples. See, you have physics is not in the textbooks. It is a way of life. If you think physics is a way of life, physics is everywhere. Physics is in the kitchen. Physics is in the drawing room, right? Everywhere. So if you draw those examples from the daily experience, then of course you can make physics interesting, the teaching of physics interesting. How I understand the nature, of course physics after all is what? Understanding nature, right? So in fact the Professor S. Chandrasekhar, the Nobel laureate, says a physicist works for pleasure and not for money. So understanding nature gives you pleasure, and therefore if you understand nature, it is easy for you to explain to students and make them interesting. So I cannot, there cannot be a regular formula for the making physics classes interesting like that. It is all purely individualistic. Of course, this is interference. You are all familiar with that. And why interference? What is interference? It is a variation or change in intensity of the light when two or more waves overlap. And during overlapping, there are different conditions. If they have identical phase and identical wavelengths, then you get the fringe pattern. And if you have, they are called coherent sources, and the properties of coherent sources. And one of the most important coherent source is the laser, right? And there, in fact, lasers have one important property, as you are all aware of. They have monochromatic radiation, and also the phases of all the photons will be the same. And that is why the energy of the laser beam is very high. It can pierce through metals, things like that, because of the high energy. Okay. Oh yes. So in fact, these are the interference expression for interference and so on. Anyway, See, this is the double slit experiment. One of the most important experiments. This double slit experiment, in which we treat light as a wavefront starting from a single slit, is passing through two slits which are close to each other. Of course, the distance of them is very small. And then from these two, you get secondary waves or wavefronts, and they overlap and give the alternate dark and bright fringes. In fact, this is a very interesting situation where, if you think of interference phenomenon, it shows that light plus light under some condition become darkness. Light plus light is darkness. More light is there, right? But see, under certain conditions, when the phases are opposite, when if you have two waves of the same wavelength and going in opposite phases, it is possible that they disappear, and if the phases are opposite, you get darkness. So light plus light is dark, just like sound plus sound is silence. Right? The resonance you have seen. So in the case of sound waves, for example, if you imagine a sound wave and another sound wave going in the opposite direction, you have positions where there are nodes. At nodes, there is no vibration. No vibration means no energy. No energy means no sound. So there are two sound waves going on, right? But they produce no sound. So sound plus sound is silence. Right? So thank you very much.
Sir, one last doubt.
Yes, sir.
Sir, the speed of light is 3 into 10 power 8 meter per second. ಲೈಟ್ಗೆ ಏನು ಅರ್ಜೆನ್ಸಿ ಇದೆ ಅಂತ ಅಷ್ಟೊಂದು ಫಾಸ್ಟಾಗಿ ಹೋಗುತ್ತೆ. ಈಗ ನಾವು ಈ ಪ್ರೋಗ್ರಾಮ್ನ ಅಟೆಂಡ್ ಮಾಡೋದಕ್ಕೆ ನಮ್ಮ ವೆಹಿಕಲ್ನ ಫಾಸ್ಟಾಗಿ ರನ್ ಮಾಡ್ಕೊಂಡು ಬರ್ತೀವಿ ಜಸ್ಟ್ ಟು ಅಟೆಂಡ್ ದಿಸ್ ಪ್ರೋಗ್ರಾಮ್. ನಾವು ಸ್ಪೀಡನ್ನು ಜಾಸ್ತಿ ಮಾಡ್ತಾ ಹೋದರೆ ಟೈಮ್ನ ಸೇವ್ ಮಾಡ್ತಾ ಹೋಗ್ತೀವಿ. ಸೊ ಲೈಟ್ಗೆ ಏನು ಅರ್ಜೆನ್ಸಿ ಇದೆ ಅಷ್ಟೊಂದು ಸ್ಪೀಡ್
ಲೈಟ್ನ ಕೇಳಬೇಕು. Because
ವಾಟ್ ಇಸ್ ದ ವರ್ಕ್ ಇಟ್ ಇಸ್ ಡೂಯಿಂಗ್?
no, it is not the question of work. See, why we can say how things are happening. Sometimes it is difficult to answer questions like why. Now, there are two, in fact, Bridgman, you might have heard of Bridgman, who is responsible for high pressures, gives a set of the questions and calls them as meaningless questions. See, why the force of gravity is always inversely proportional to the square of the distance. Why the force between two charges is inversely proportional to the square of the distance. Coulomb's law. Why? See, the statement is there, you have made the observation, and from observation, experimental observation, you have come to the conclusion. Why it is happening? Why gravity is there? So, science to some extent explains certain things of how things are happening. That is what we observe in nature and how things are happening. But why such things are happening? Why there is gravity? Of course, later on, Einstein gives an explanation for that. Curvature is nothing but gravity. But till then, till Einstein, 1916, nobody knew about the reason for gravity. Why there is a gravity like that? So, of course, you have a challenge. That is a very interesting question. You have a challenge. Why light has urgency? If you establish the reason for that, I am sure you will get a Nobel Prize.
Because of our inability to explain, we assume that light is having both.
No, it is measured. Of course, light measurement of the velocity.
Dual nature ಅಂತ ಹೇಳಿದ್ರು. It's an inability to explain the exact nature of the light. That's why it possesses the dual.
No. Whatever is observed, in fact, as Professor Govinda mentioned, physics is measured.
ಇವಾಗಿನ ನಾಲೆಜ್ ಪ್ರಕಾರ ಅದನ್ನು ಮಾಡೋದಿರ್ಬೋದು, ಮುಂದೆ ಅದು ಬಂದೇ ಬರುತ್ತೆ. ಆ್ಯಸ್ ನಾಲೆಜ್ ಡೆವಲಪ್ಸ್ ಅದು ಬಂದೇ ಬರ್ಬೋದು ಅದು.
Now, see, physics, as Govinda mentioned, is measurement. If you cannot measure a physical quantity, see, all physical quantities are measurable quantities. Of course, I may take 2 minutes extra. All physical quantities are measurable quantities.
Hello, sir.
The quantities which cannot be measured are not physical quantities. For example, intelligence. You cannot have a meter to measure the intelligence. Intelligence is not a physical quantity. But temperature, mass, volume, they are all. So, in fact, Kelvin says that if you cannot measure any quantity, then it means that you have not understood it. Right? So, you have measured the velocity of light, it has a certain value. Why it has a certain value, there is no answer for that. So, a set of, meaningless questions as Bridgman gives, in fact, why there is, and also you notice that we have in the universe, as far as our knowledge goes, we have 3 dimensions in space, only 1 dimension time, x, y, z and t. To measure any object, the object has a certain spatial position, and it is given by x, y and z. And at a given time it is there. So t, x, y in nature we have 3 dimensions in space and only 1 dimension in time. It is unsymmetric. So all these are all meaningless questions which have no answer at this point. Thank you.
ಥ್ಯಾಂಕ್ ಯು ಸರ್. ಮಿತ್ರರೇ, ನಮಗೆ ಸಾಕಷ್ಟು ಪ್ರಶ್ನೆಗಳಿದೆ, ಆದರೆ ಸಮಯದ ಅಭಾವದಿಂದ ಈ ಸೆಷನ್ನ ಇಲ್ಲಿಗೆ ನಿಲ್ಲಿಸ್ತೀವಿ. ಇದುವರೆಗೆ ಪ್ರೊಫೆಸರ್ ಜಿ ವೆಂಕಟೇಶ್ ಅವರು ತಮ್ಮ ಅಪಾರವಾದಂತಹ ಅನುಭವದ ಮೂಲಕ ಪಡೆದಂಥ ಜ್ಞಾನವನ್ನು ನಮ್ಮ ಜೊತೆ ಹಂಚಿಕೊಂಡಿದ್ದಾರೆ. ಅವರಿಗೆ ನಮ್ಮ ಬೆಂಗಳೂರು ಪ್ರಾಂಶುಪಾಲರ ಸಮಿತಿಯ ಪರವಾಗಿ ತುಂಬು ಹೃದಯದ ಧನ್ಯವಾದಗಳನ್ನ ಸಮರ್ಪಿಸ್ತೇನೆ. ನಮ್ಮ ಒಂದು ಸಣ್ಣ ಕಿರುಕಾಣಿಕೆಯನ್ನು ಸ್ವೀಕರಿಸಬೇಕು ಅಂತ ಕೇಳ್ಕೊಳ್ತೀನಿ ಸರ್. ಭೌತ ವಿಜ್ಞಾನ ಅಧ್ಯಾಪಕರ ವೇದಿಕೆ ಹಾಗೂ ಪ್ರಾಂಶುಪಾಲರ ಸಂಘ ಬೆಂಗಳೂರು ದಕ್ಷಿಣ ಇವರ ಸಂಯುಕ್ತ ಆಶ್ರಯದಲ್ಲಿ ನಡೆದಂತಹ ಈ ಕಾರ್ಯಗಳನ್ನು ತಮ್ಮ ಅನುಭವವನ್ನು ಹಂಚಿಕೊಂಡಿದ್ದಕ್ಕಾಗಿ ವಿಶೇಷವಾದಂಥ ಧನ್ಯವಾದಗಳು ಸರ್. ಇದಾಗುತ್ತಲೂ ಹೊರಗೆ ಹೋಗುತ್ತಲೂ ಪಕ್ಕದಲ್ಲಿ ಕ್ಯಾಂಟೀನ್ ಇದೆ, ಅಲ್ಲಿ ಕಾಫಿ ಟೀ ವ್ಯವಸ್ಥೆ ಆಗಿದೆ. ಅದನ್ನು ತಗೊಂಡು ಎಲ್ಲರೂ ಸ್ವೀಕರಿಸಿಕೊಂಡು 12:10ಗೆ ಎಲ್ಲರೂ ಇಲ್ಲಿ ಗ್ಯಾದರ್ ಆಗಿ ಮುಂದಿನ ಸೆಷನ್ನು ಪ್ರಾರಂಭ ಆಗುತ್ತೆ. ನಮಗೆ ಇವತ್ತು ಫಿಸಿಕ್ಸ್ ವರ್ಕ್ಶಾಪ್ ನಡೀತಿತ್ತು, ಅದಕ್ಕೆ ಹಾಗೆ ಎತ್ತಲಿಕ್ಕಾಗಿಲ್ಲ.